So good afternoon. Welcome you to participate in the open seminar in Frontier of Nuclear Physics. I am Yigang Ma from Fudan University. Today, we are very happy to have the 42nd seminar of this series. The present seminar will be given by Professor Francesca Gulminelli from LPC as well as the University of Caen. She is one of very active nuclear theorists in our nuclear physics community, and this seminar series is hosted by Fudan University as well as Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. The seminar is also co-organized by the Journal of the Nuclear Science and Techniques, as well as its Chinese edition, Nuclear Techniques. This seminar is also open for the public in nuclear physics community, and the seminar is also live shown by the Koshie.com. So before this seminar, I would like to introduce the speaker, Professor Francesca Gulminelli. Francesca is an exceptional class professor at the University of Caen. She received the PhD in physics at the University of the Milano, Italy in 1992 and joined the University of Caen since 1994. Her main research interests lie in theoretical heavy ion physics, including transport theories, statistical mechanics of the phase transition, theoretical nuclear astrophysics and analysis, and the interpretation of the nuclear data. Now, she serves as the head of the theory group of LPC laboratory and the head of the master program in physics at Caen. She has published more than 180 articles and received awards such as the Julie Curie Award of the Flying Physical Society and the Outstanding Review of the American Physical Society and the Institute of Physics, England. And so today she will give a talk on the detectability of a first order phase transition in the dense matter. So let's welcome Professor Francesca Gulminelli. So please.
Thank you very much, Yigang, for the nice presentation, and thank you very much for the invitation. It is a pleasure for me to be with you today and to elaborate on the possibility of detecting a first order phase transition from hadrons to quarks in the core of neutron stars, phase transition that it is hoped to be accessible through gravitational waves observations from third generation interferometer. So first of all, a few words of motivation of this work. Why gravitational waves? I think this is something which is known to all of you. The reason is that the recent detection of gravitational waves by the LIGO Virgo collaboration has opened the possibility of a direct measurement of the QCD phase diagram we are all interested in, and more specifically the high density part of that. Is low temperature and high density there, where a first order phase transition to quark matter is expected. So this is really very exciting because it is the first time where there is this opportunity of a direct measurement. And when I say direct, I really mean it because, as I think everybody knows, the general relativity theory imposes a one-to-one correspondence between what we call the nuclear equation of state, that is the functional relationship between the pressure and the energy density in stellar matter, and the static properties of neutron stars. In this very famous picture from Jim Latimer of more than 10 years ago, the correspondence is shown for the mass-radius relationship of the neutron star, but this same correspondence is true for any other static properties, and particularly the relationship between the mass and the tidal polarizability lambda, which is the quantity that is measured by the gravitational waves. So what does it mean? This means that if we imagine two different compositions for the neutron star, in this picture here, the solid line, it was a hadronic equation of state, only hadrons, and the dashed line, it was a quark equation of state, only quarks, then this, in principle, is going to lead to different mass radius or mass lambda relations, and therefore to different gravitational signals. So all this is very exciting, and the whole community is excited since a few years, since the first discoveries of gravitational waves because of that. But of course, there are problems, there are difficulties, and the problems that I want to share with you are all twofold, are both experimental and theoretical. So from the experimental side, the problem of that is the fact that this tidal information, lambda information, is not direct. So let me explain you a little bit, if you're not familiar with what is the information that is extracted from the gravitational waves. This information is a modification of the gravitational waveform with respect to what is expected from general relativity of 2 point-like objects that fuse. Modification that is happening at the very late time of the merging, just before the merging, which corresponds to a very specific high frequency domain here in the gravitational wave, and which is due to the deformation of the neutron stars due to their mutual gravitational field. So their mutual gravitational field induces a quadrupole moment. And as you know, it is quadrupole deformation that produces the gravitational waves. And this quadrupole moment depends on the field of the companion star, and therefore on the compacity of the companion star through a coefficient, which is this lambda coefficient, this tidal polarizability that depends on the compacity and therefore on the radius, and it encodes all the information about the equation of state. Very good. So where is the problem? The problem is that there are two objects here, two neutron stars that are not necessarily the same mass. So this means that they have two different tidal polarizability, lambda 1, lambda 2, or what the experimentalists do is they define lambda tilde and delta lambda tilde via a linear transformation. And these two coefficients, in principle, should be extracted from the very same waveform. But this extraction comes from a modification of the phase of the waveform. And the two coefficients, the lambda tilde and the delta lambda tilde, they appear at two successive orders in the post-Newtonian expansion of the waveform. This x is a small parameter, so this means that it's small effect, small modification of the waves, and the delta lambda tilde appears at the sixth post-Newtonian order, the lambda tilde at the fifth. So practically, this means that this thing is not accessible from the data. And the first term, that is the lambda tilde, this is measurable, but with big error bars. So the net effect is that, in principle, this lambda tilde should be a number that depends on the combined masses and radii of the two stars. And in practice, this is a whole distribution which is pretty large because of this finite sensitivity of the instrument. So this is from the experimental side. From the theoretical side, the problem is probably even bigger. This is because, as you all know here better than me, there exists no ab initio theory of dense matter, only effective models of QCD. And if we want to describe stars with the phase transition to a quark core, this is hybrid stars. This means that you need to describe something that it is hadronic at low pressure, and then a quark deconfined at high pressure. And so you need two different effective models for the hadron part, nucleonic equation of state, and for the quark part. And all of these are not ab initio calculations, but are effective models of QCD. And you can see here, if we just look at the quark part, this is the least known one. And according to the different models that you can employ to describe this high density part, this can lead you to very different mass radius, or we are specifically interested in this mass lambda relation. So you see that the possible behaviors are all these colored lines, and they cover more or less for a given mass, a very, very large range of possible tidal polarizability. So there are huge uncertainties on the quark side. The hadronic side, in principle, this is our job as nuclear physicists. So in principle, this is something that is better constrained, but still this is not as true as that. There are also very huge uncertainties on the hadronic side. This means that even if this quark chemical potential is high enough that indeed the transition is not met at the pressure, at the highest pressure that exists in the core of the neutron star, maybe the transition is too far away, we cannot see it. Maybe the star is purely nucleonic. In that case, we know better the relation between lambda and m, but still there is a model dependence that depends on the nuclear model, and this model dependence is still larger than the experimental measurement. So it's even less precise than the experimental measurement. Because of that, this is the present status of the situation. I already showed you this lambda tilde distribution that is extracted by the analysis of the waveform from the LIGO Virgo event GW170817, which is for the moment the only one for which we have a measurement of the lambda. Here it is. And here you can see all the big variety of the different models. The gray distributions are hadronic models. I also plotted two among the forest that I showed you before of those hybrid models, hybrid equation of state, just two of them. And so what you can see here is that from a measurement, which is this blue distribution, there is absolutely no chance to discriminate between the different models. So this is the present status. And then what are the questions? How can we progress? So the first thing is that I show here lots of models. We can see here that a model like that one is in contradiction with the experiment. Okay, so we can throw it away. But maybe there are many other models that can be eliminated on other arguments that simply this measurement. So the first question is, are those models all good, or which are the good models? Maybe not all of them are consistent with the whole bunch of experimental information that we have. The second question that we have is, I'm showing here like 10 curves. I could show you 100 or 200. So where should we stop? Is the ensemble of models exhaustive of all the possibilities of hadronic matter? And then finally, imagine that we are able to pin down the exhaustive ensemble. Imagine that we are able to pin down the good models, and imagine that we are left with this PT03 and this APR4, for instance. they predict a very, very close lambda polarizability, and therefore the question is, will we be able to discriminate the models with the phase transition from the models without the phase transition? And this is a question of model, but it's also a question of experiment, because if they are close away, we need a very precise measurement. So this is the kind of questions that I want to address in this talk. And as a nuclear theorist, my focus will be on the theoretical side and on the fact, on trying to solving these two first problems. That is, what we need is a general modeling, a modeling that can include all the different possibilities according to the two hypotheses that we want to discriminate. We want to discriminate the hypothesis of an hadronic neutron star with respect to the hypothesis of a quark core. So we need something like a meta modeling of nucleonic and of non-nucleonic matter. So let's start with the low density part, the nucleonic part, because this is in principle easier. There are less possibilities there. And so what we have been doing in the last years is something that we call the nucleonic meta-modeling. That is a development of the most general equation of state under the hypothesis that matter is, baryonic matter is only composed of neutrons and protons. What does this mean? This means that to introduce a functional, an energy functional, that depends in the most general way as we can on the densities at their derivatives, density of the correct degrees of freedoms, that here are neutrons and protons, and the functional that is flexible enough that it can reproduce all these different effective models that I showed you before, and that can also interpolate among them and produce other dependencies, density dependencies that are not explored yet. So to do that, one needs parameters to have this flexibility. And those parameters, so we have 18 parameters that comprise both bulk and surface properties of nucleonic matter. And those parameters have to be explored. This is a huge parameter space, very, very huge parameter space that has to be explored in the most agnostic way as possible, such as not introducing any bias, in such a way that we can span the uncertainties which are underlying this hypothesis that matter is only composed of neutrons and protons. This is the advantage of modeling the energy directly, instead than the pressure, as a function of the density of neutrons and protons, is the fact that you can, of course, if you impose infinite matter and bit equilibrium, you can have the equation of state of the neutron star. But at the same time, you can also have a model for finite nuclei. And this means that once you have constructed all your possible models, you can construct observables that pertain to the finite nuclei on one side, radii, binding energy, on the astrophysics on the other side, mass, radii, lambda, polarizability, and you can put constraints that come from theory or experiments from both worlds. You can condition your posterior distribution on both astrophysics and nuclear physics observables. So this is the idea. And the kind of constraints, the kind of posteriors that we apply are listed here, the nuclear physics side and the astrophysics part. I'm going to concentrate more on the nuclear physics because of the audience. Anyway, this is going to be both data and theory from the nuclear physics side. From the astrophysics side, this is going to be everything that we have up to now, that is radio timing information, gravitational waves information, and X-ray information. And all this information is implemented in the posterior distribution of parameters with the standard Bayesian techniques. In that way, once you construct this most general equation of state that reproduces all the different constraints that you have, the hope is that this prediction is going to be not as spread as what I showed you before, but it's going to be relatively precise, such that if you have a measurement and this measurement does not comply to that, this is a proof that you need some new physics, that the nucleonic hypothesis is not enough. So this meta-modeling, this acts as a null hypothesis for exotic degrees of freedom. Okay, so how to do in practice? I don't think I want to go really pretty much in the details, because this is going to take us time and maybe it's going to be boring for some of you. If you want, maybe we can discuss afterwards. The technical details, what I want to stress is the fact that we describe the finite nuclei with the extended Thomas Fermi approximation parameterized density profiles. The infinite nuclear matter, we have parameters that describe the density dependence with the usual empirical parameters like compressibilities, asymmetry energy, and stuff like that. But we also have effective masses and surface terms, isoscalar and isovector, such that we can treat in a unified way the crust and the core, and we can describe, as I told you already, finite nuclear observables and equations of state in a unified with the same functional and the same at the level of equality. So what we can we describe specifically from nuclear physics? I told you experiments and theory. So first of all, theory. The constraints from nuclear physics, as you know, in the past maybe 10 or 15 years, nuclear theory has done a very huge progress thanks to the possibility of describing the effective interaction through the chiral interactions, because those chiral interactions are constructed with a diagrammatic expansion, which allows you to evaluate the uncertainty of the prediction in a controlled way. And at the same time, there has been progress in the many-body technique to deal with that. And so we have different ab initio techniques, many-body perturbation theory and quantum Monte Carlo kind of theories. And all of this gives predictions with controlled uncertainties at low density, up to a certain density, because the power counting, which is implicit in this chiral interaction, implies a validity up to a certain density, which means that imposing this kind of behavior, this is pure neutron matter, the function of density, energy per particle. Imposing this kind of behavior is going to constrain us the parameters that are linked to the low density behavior of the equation of state, but it's not going to constrain us everything which is connected to the high density. So this is theory. What about experiments? There are different observables from nuclear physics: masses, radius, skins, collective modes, polarizability, isobaric analogous states, flows, and so on and so forth. Some of them need, as you know, complicated dynamical treatments, like the flows, like the polarizability, response, RPA, transport codes, stuff like that, which induce extra systematic errors. So what we have been doing up to now is to concentrate just on the observables that are available only within the functional, without extra assumptions on the many-body dynamics. And this is masses and radii. And those, again, are only sensitive to low density, and so are going to constrain low density parameters. So you may feel that this is a little bit limitative to have only masses and radii, but still, what I want to stress is that the constraints for nuclear experiments are still very important. and very complementary with respect to the constraints from nuclear theory. This is shown here. Here I'm showing the energy and the pressure of infinite matter, pure neutron matter up, and symmetric nuclear matter down. And in blue is the range of behaviors which are compatible at 95% probability with the constraints that come from experiments, and in pink, the ones that come from the theory. And what you can see is that in pure neutron matter, experiments are not very performant indeed, and it is the theory that really guides us. But as long as symmetric nuclear matter is concerned, the constraints from experiments are more constraining than what comes from the theory. So it's important to have them both. These are the results. These are the results for the neutron star observables. So I told you what we need to construct any static observable as a neutron star is the equational state, pressure as a function of mass density. This is the prior equational state that is obtained by varying in a very large way all our 18 parameters and imposing only very basic conditions like causality and thermodynamic stability, this yellow one. And then what you see here is what happens when you impose the constraints that come from nuclear physics, both theory and experiments. And what you see is that the low density part up to saturation density becomes much thinner than in the initial distribution, much better constrained. In this figure here, you see what happens when you apply the constraints that come from the astrophysics. I have not described you in details, but the masses and radii in astrophysics. And what you can see here, it is the intermediate density part, let's say, that becomes more constrained. And so at the end of the day, the final pressure versus density, which is compatible with this nucleonic hypothesis, only neutrons and protons as baryonic degrees of freedom, is this final surface here, which is relatively well constrained, and which in terms of mass radii of neutron stars is reported here. This is this colored surface, and it is compared to the different astrophysical measurements that we have up to now. This is the nicer measurements from the X-rays, and this Abbott, this is the famous 1708-17 gravitational wave signal. And here in the different lines are the single predictions of single models that have been developed by the different nuclear theorists over the year, and just a selected number of them. And what you can see here is two things. The first thing that you can see is that the nucleonic hypothesis is compatible with all the present observations. There is no evidence that we need any quark in the core. And the other thing that you see is that if there are models which have been developed that are maybe still quite popular, but that can be considered as marginal in the sense that they are not compatible with the total amount of constraints that we have from nuclear physics and astrophysics together. This is mass radius. In reality, what is the most direct observation is the tidal polarizability. I already showed you the experimental distribution. It is this one. And this is what comes out from this meta-model analysis. This single observation, 1708-17, as I told you, can only give you combined information, not on the two stars separately, but on the combined, so the chirp mass and the asymmetry. This is the ratio between the masses of the two, and it is quite a large distribution of this asymmetry. And so this is the combined distribution in the lambda tilde and asymmetry plane, and this is the projection on the lambda tilde. So when you compare it to the measurement, this is the prediction of the nucleonic hypothesis, And again, you see the same thing as before. Nucleonic hypothesis is compatible with the observation. You see with this blue surface. And there are some hadronic models which are not compatible with what we think is the nucleonic hypothesis. That is, they can be considered as marginal. Okay, so this is for standard hadronic stars. And now, what about the possibility of having quarks in the core? So hybrid stars. So hybrid stars, something which is non-nucleonic, is quite vague. In reality, there are lots of possibilities for new degrees of freedom. And it's so vast that I'm not able to consider them all as a bunch. So I'm going to consider something which is very approximate and limitative. That is the simplest scenario of a first order phase transition to quark, of a first order phase transition, yes, from hadronic to something else, to something exotic, such that the low density phase is described by this model that I showed you before, this nucleonic meta-modeling. And the high density phase, since I don't know exactly how to describe it, I'm going to take an agnostic way, which is just a simple constant sound speed model. This means that for the quark phase, I have 3 additional parameters, which are listed here. The density at which the transition occurs from the hadronic phase to the second one, the width of the plateau of the first order phase transition, and then the high density behavior parameterized as the asymptotic sound speed. Those 2 CS and delta epsilon, we take them again as agnostic as possible. So a very large prior, flat and large, exploring many different possibilities. And while the transition density, what I'm going to show you is 3 different hypotheses with discrete values. An early phase transition at 0.3 Fermi minus 3, a late phase transition 0.445 Fermi minus 3, and something in between 0.4. So for each of these 3 hypotheses, considering all the possible variation of the width of the plateau and the sound speed, you have lots of different possible behaviors for the equation of state, pressure versus density here. And then those, again, those bunches, those samples of equations of state are confronted with the different constraints I showed you before. Since this is high density, it's essentially the astrophysics constraints that matter, and nuclear physics is not effective in constraining that. But still, this modifies these distributions from the my prior, and we're going to have posterior distributions according to the 3 different hypotheses of the density of the phase transition. So this is the result: mass radius and lambda mass for the hybrid equations of state with the 3 different families, the red, blue, and green, corresponding to different densities at which the phase transition occurs. And they are compared. I'm sorry, this is not very, very visible here. This green light band, I hope you see it. This is the nucleonic hypothesis that I showed you before. What you see here is that if you look at the lambda here, if you have like a very high lambda, then you see that all the different hypotheses have the same prediction, so you cannot discriminate. But in principle, for a like canonical neutron star, a low lambda is something that is compatible with an early phase transition, but is not compatible with the nucleonic model. So in principle, you can discriminate. I say in principle because, again, what you are measuring is not one value. You are measuring a whole distribution. And we already know that presently a difference like that, this is not something, this is pretty well within those error bars. So this is not something that is detectable today, but maybe this can be detectable tomorrow. And why that? Because I told you at the beginning, the reason why this measurement is a large distribution is because it is due to those tidal effects. Those tidal effects in this amplitude versus frequency plane, they occur just before the merging, so at very high frequency and low amplitude. And this comes very close to the sensitivity of the instrument. So there is a huge signal to noise ratio. But there are projects both in the US and in Europe, and there is this Einstein telescope, there is this cosmic explorer, which are third generation interferometers that are going to have sensitivity curves which are much lower, which means that the signal to noise ratio in this frequency band is going to be much thinner. And this is and so the question is, will this be enough to recognize the phase transition, considering that the analysis is very, very subtle? And so this is the last thing that I want to show you, how those different predictions can compare to potential future observation through the Cosmic Explorer or through the Einstein telescope. And to do that, what we have done is the following. We make the hypothesis that the star is indeed a hybrid, that there is a phase transition at a certain density, just to be simple, fixed density. And so this is our hypothetical event, and we consider an hypothetical observation with the given chirp mass, with the given mass ratio, so two different masses, and at a given distance from the observer. And consider that we have this merging event that is detected. Given a mass, chirp mass, a mass ratio, and the distance, well, the distance is not needed. Given a chirp mass and the mass ratio and the NEOS model, this gives you a lambda tilde and a combined polarizability. Then, of course, this signal has to be interpreted through a waveform, and so there is the interferometer sensitivity that enters in the game, and this we take into account with a simple Fisher matrix treatment that is a publicly available tool. It's called the GW bench, that allows you, according to the sensitivity of the interferometer, to compute the distortion of the observables, including the lambda tilde. And this is going to depend on the distance, on the sky localization and stuff like that. And so a single lambda tilde gets distorted into a distribution. At the same time, you have two hypotheses: the nucleonic hypothesis and the hypothesis which in principle is the correct one, the one that corresponds to my input data, that is that there was a phase transition, and each of them predict a distribution of lambda tilde in the way that I showed you before. And here is how those three things compare. So you see, this is an hypothetical observation which is very close by. The GW 1708-17 was at 46 megaparsec, so quite close by. And the injection model is so the input model assumes an early phase transition at 0.3. So the measurement is going to be very precise. The distribution is very thin, this red, and you see it is, of course, very well compatible with the general behavior that we predict for a phase transition at this density value. On the other side, the hypothesis of a purely nucleonic behavior is this blue, and you can see that this can be excluded from the measurement. So if this is the situation, we are in business. It's the two things can very well discriminated. This is due to what? This is due to the fact to two things in reality. This is due to the fact that we are considering an observation that is very close by. On the opposite idea, if we imagine that the observation is very far away, then of course the measurement gets red. This is the measurement, it gets red. It is still compatible with the hypothesis of the phase transition, but the hypothesis of the nucleonic content is the blue, and this becomes so spread, then you see it's going to be difficult to exclude it from a measurement like the red one. same difficulty arises if the observation is close by, but if nature decides that the phase transition occurs later, if the phase transition is at a very high density, then the two theoretical predictions with and without are so close that even if the measurement is very precise, it's going to be difficult to discriminate between the blue and the green. So this is just a visual thing. It can be quantified better by calculating bias factors that are defined like that quantify the probability of discriminations of the two different hypotheses, the phase transition one with respect to the nucleonic one. And this is how those bias factors behave as a function of the distance of the imaginary observation and as a function of the other parameter that we saw as very important, that is the density at which the phase transition occurs, 0.3, 0.4, and 0.5 Fermi to the -3. And so what you can see is that a very late, to discriminate the hypothesis, you need to have a positive log of B, bigger than 1, something like that. And so you can see that this is never achieved if the phase transition is very late. While if the phase transition is early here, this is not achieved if the observation is far away, but it's very well achieved if the observation is close by, and close by not only 22, but even further away than that. Which means that there is, with future interferometers, a high detectability potential of this density jump, whatever the width of this density jump, because for us this was a free parameter that was largely varied, if the phase transition is early enough. And this brings me to my conclusion, summary and conclusion. So the question that I have asked in this seminar is how is it possible to prove or to disprove, because nobody knows indeed what is happening in the core of neutron star, to prove or disprove the existence of deconfined matter in the core of neutron stars. And what I have proposed to you is something like a null hypothesis, that is a meta-modeling technique of the hypothesis that matter is composed of neutrons and protons, that allows predictions with controlled uncertainties. And doing that, our present conclusion is that looking at everything that we have as present astrophysical observation, there is no indication of exotic degrees of freedom. However, this using constraints that come both from astrophysics and also from nuclear physics, we have a prediction of observables which is relatively tight, which means that potentially there is the possibility of challenging this hypothesis. And in particular, I've shown you, well, just a toy exercise of a simple, the possibility of detection just of a density jump and first order phase transition, and try to convince you that this density jump can in principle be detectable with the new generation interferometer, which is the post-05 for the LIGO Virgo collaboration and the Cosmic Explorer and the Einstein telescope in some 10, 15 years ahead. And with this, I thank you very much for your attention. Show you my collaboration in red, the students. And if you have any questions, I will be happy to try to do my best to answer.
Okay, so thank you, Francesca, very much for your nice talk and give a very clean presentation. So now, any questions from the online?
Can you hear me? I have a question.
Yes.
Yeah, there is a recent pulsar observation of our neutron star with a mass of 0.77 solar mass. with a radius around 10 kilometers. How does that affect your analysis?
Yeah, well, as you know, this observation is questioned a little bit. But if an observation like that is confirmed, do I have? I in principle I have. Do I have this? Yeah, you see, for instance, this is how an observation of a neutron star of mass. Well, this is not the observation you are speaking about, but the effect is the same. This is how an observation of a mass of a pulsar of a mass 2.5 would modify the results. In itself, the fact of having, well, I don't have a picture with exactly what you are asking for, but the fact in itself of having a high mass and a relatively small radius depends a little bit on the error bars and so on. This can be accommodated on the nucleonic hypothesis, but then you get through a contradiction with the other observations. That is, you can see here, this is the inside these dashed lines. This is the gravitational wave signal. And then if you include as extra constraint the possibility of having these high masses, then this does not get compatible anymore with the gravitational wave signal. So indeed, you are absolutely right. An observation like that, unfortunately, we cannot comment it. So we will have to hope that this happens. But an observation like that, if it is confirmed, would be a very, very, very strong argument in favor of exotic degrees of freedom.
That observation is a very low mass with a small radius. I just wonder your meta modeling
small mass. Sorry, small mass. I thought that there is a pulsar. There is, a 2.55 pulsar which is discussed. No, low mass. Sorry, low mass and small radius.
Yeah. Yes, that one.
Sorry. I misunderstood you.
Yeah, that's 0.3 solar mass, I think.
Yeah, well, 0.3 solar mass.
0.77 solar mass.
0.7 solar mass and small radius.
10 kilometer radius.
Yeah. Something like that. Yes, this goes out of everything. Indeed, yes. I'm not convinced that the pulsar can be 0.7 solar mass. But let's see. Yes. Thank you.
You mean that observation need a further confirmation, a further approach? That observation is suspicious.
This is what I heard. I mean, I'm not an astrophysicist, but this is what I heard. Yes.
Oh, okay. I see. Thank you.
Yeah.
Hello. Yeah. Hi, Professor. Thank you very much for the nice talk. As you mentioned, for the first order phase translation, there is a jump in the baryon density, and besides in the first order phase translation, there will be a mixed phase, and there will be mechanical instability. So I would like to ask what's the role of the mixed phase of the mechanical instability on the gravitational wave?
Yeah. Well, on the static observation, that is just this lambda polarizability. This is going to make a behavior which is smoother than the jump, because this is going to make a continuous phase transition. So this is something that is going to, if it is like that, this is something that is going to enlarge the signal and make the distinction with the nucleonic hypothesis more difficult. On the other hand, if the phase transition occurs only during the merger. The instabilities that are there, they can certainly affect the post-merger signal. And this, well, requires very sophisticated hydrodynamical calculation, but it's a very interesting issue. It would be a very interesting issue. This would not be seen, the instability itself, the mechanical instability would not be seen in the tidal polarizability, but it could, I guess I have not done any calculation like that, but I think in principle could be seen in the post-merger signal. Do I answer to your question?
Yeah, so yes, thank you very much for your explanation. So do you think is it worthwhile to carry out such investigations on the mechanical instability on the gravitational wave signal from neutron star merger?
Okay.
Yeah. Okay. Thank you very much for your nice explanation.
And what do you find? Send me your paper. I would be very happy to study it. If you have, you are studying the waveform that comes from the modification to the waveform that comes from the presence of mechanical instability. This is what you are telling me.
We are working on that, but we haven't have obtained the final result yet. Yeah, if we had the result, I would be happy to send it to you.
Yes, please.
Yes. So, any more questions? So we still have some time.
I have another question. There is a PREX experiment measurement of that L parameter. It shows it obtains a very large L parameter. I wonder, in your meta modeling, when you consider the experimental constraints, you are using the large L or some small L that of previous measurements or the PREX measurements.
Our parameter, I didn't understand.
So I think he. I think he is talking about the parameter for the equation of the state, maybe like a slope parameter or skewness parameter.
Yes.
Yeah. So the equations of state parameters are those things that I call the X bulk. So these are the usual stuff, the derivatives at saturation of either symmetric matter or of the symmetry energy. And those parameters, well, I don't have a picture here, but the prior of these parameters is extremely large. So you can explore, so the L parameter, maybe this is the symmetry energy slope you're thinking?
Yes. I think so.
Okay. So let me see, maybe I have something compared with the PREX that I can show you.
Yeah, they get a very large the slope, which is a little contradictory with previous experiments.
Yeah. So that's it. Okay, this is, you want to see the comparison with the PREX? Yes.
Yeah, PREX. Yeah.
So I don't have I have also the distribution of the L. So you see, this is it. This is what you see. So what we have done here is that we have we have not calculated. This PREX measurement is not a measurement of the L. It's a measurement, and it's not in reality even a measurement of the skin. It's a measurement of the parity violation scattering, and then you need a model to transform this into a skin, and you need an extra model to transform this into an L. Now, the parity violation scattering, I'm not able to compute it with this model, but I'm able to compute the skin. So what we calculate is the skin. So this is of the lead. So this would be the PREX, and of the calcium, this would be the CREX. And then this blue thing is the 1 sigma result of the PREX paper, 1 sigma result of the CREX paper. And then what we can do is that we compare to the measurement, or we believe to the measurement and we take it as a constraint. So if we don't believe to the measurement, we just take it as a constraint. This is what we get. So you have to look at the like you see this blue is our prediction for the skin when we consider the theoretical filter, so the chiral EFT calculations, and you see that this is not compatible with the PREX, while this is compatible with the CREX.
So you are saying the PREX is not trustable. Their results is not trustable.
Well, let's say that they themselves, they say that they are analyzing the data. Anyway, or there is an incompatibility of those two things in terms of skin. If it is, then we can say maybe this is trustable, and maybe this is it is the theoretical measurement that is not correct, theoretical calculation. So if I put PREX as a constraint, if I apply it to my filters, then this is what I get. This is the blue. And if I use the CREX, this is the yellow. So you see that there is a little tension even between the two measurements, between the yellow and the blue. They are not as compatible as that among themselves, but still, if you want them, both of them, then this is the green. Okay, so this is, of course, this is Bayesian analysis. If you believe if a measurement is true, then you apply it, and this is going to shift your prediction. So our prediction, if we apply PREX as a constraint, of course they are compatible with PREX, and this is it. And then the question is, are they compatible with the chiral EFT? This is a problem of either the PREX people or the chiral EFT people. You see.
I see.
The incompatibility is more among the theoretical chiral EFT calculation and the result of the PREX. For us, if we include the PREX as a constraint, then you see this does not modify as much the tidal polarizability or the radius. So you can see you can see what it does. Where is it? With or without. This means from the dot to the blue and the red. So it modifies a little bit towards a high tidal polarizability, but not so much, because the PREX in any case is something that is going to be sensitive at low density. And therefore, at high density, this depends on the behavior at high density. But the PREX is not putting the PREX does not make you incompatible with the astrophysical information. There's no problem about that. For me, the problem is between the nuclear theory predictions and the PREX. This is at least this is what my analysis tells.
Oh, I see. Yes, thank you.
Okay. So any more questions? Yeah, I think it looks all participants yeah is very satisfied with your talk. So then yeah, let's thank Professor Francesca Gulminelli again for your excellent presentation, and also I thank all the participants from the online. Okay, so maybe yeah, let's say goodbye.